In this episode, we're going to connect a few virtualization ideas that beginners often learn separately and then struggle to combine when something goes wrong in the real world. How a virtual machine, VM, is stored, how it changes over time, how it can be moved, and how its networking is presented. A VM can feel like a single object, like a file you start and stop, but under the hood it is a small ecosystem of storage, configuration, and virtual devices that evolve as you use it. If you think of a VM as a living system with a life cycle, the confusing terms start to line up into a simple story. Images are the baseline body, snapshots are time-stamped branching points, migrations are movement of the running workload or its data, and network modes are the choices that decide how the VM talks to the outside world. Linux Plus questions tend to reward the student who can explain these relationships clearly, because that shows system-level understanding rather than tool memorization. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A strong mental model begins with storage images, because the storage image is what makes a VM durable across reboots and host restarts. When you shut down a physical computer, its disk still contains the operating system and files, and the same is true for a VM, except the disk is represented as an image on the host. That image might be a single file, or it might be represented by a set of files and metadata, depending on how the VM was created and how the storage backend is organized. The key beginner point is that the VM disk is not imaginary, and it is not simply memory. It is persistent storage that must live somewhere, be protected, and be managed. When you think about disk space, performance, and backups, you are really thinking about the storage image and the host system that supports it. If an exam scenario mentions a VM failing to start due to storage issues or a host running out of space, the storage image is often at the center of the explanation, even if the question does not use that exact phrase. Once you accept that the VM disk is an image, the next concept to understand is how that image relates to the VM's identity and configuration over time. A VM is more than its disk, because it also has virtual hardware settings such as how much memory it receives, how many virtual processors it gets, and what kind of network interface it uses. Those settings are part of the VM's definition, and they matter because they influence compatibility and performance, but the storage image remains the anchor for the operating system and the data. This creates a practical reality. You can often move an image to a new host, but you must also move or recreate the configuration that describes how that image should be attached and booted. Beginners sometimes copy only the disk file and expect the VM to appear automatically, then feel confused when the new system does not know what to do with it. In lifecycle terms, the disk image is the body, and the configuration is the blueprint that tells the host how to animate it into a running system. Snapshots are where the lifecycle becomes more dynamic, because a snapshot is a way of capturing a point-in-time state that you can return to later. Beginners sometimes think of a snapshot as a backup, but the better mental model is that a snapshot is a branching point within a storage tree, designed for short-term safety and rapid rollback rather than long-term archival protection. When you take a snapshot, the VM can continue running and changing, but the snapshot preserves a reference to what the disk looked like at that moment. Many snapshot systems do this by using a copy-on-write approach, where the snapshot becomes a read-only base and new changes are written into a new layer. This is powerful because it is fast and space-efficient at first, but it comes with trade-offs, because the VM storage now depends on a chain of layers that must be kept consistent. On the exam, if a question hints that performance degraded after many snapshots, or that a snapshot chain became complex, the copy-on-write layering concept is often the missing piece. It is also important to understand that snapshots can involve more than just disk state, and that distinction changes what a snapshot is useful for. Some snapshot approaches capture only the disk contents, which means they are good for rolling back files and operating system changes, but they do not capture what was in memory at the time. Other snapshot approaches can capture both disk and memory state, which can allow a running VM to be resumed from a frozen moment, almost like pausing time. For beginners, the The practical takeaway is that not all snapshots are equal, and you should think about what kind of state you are preserving when you hear the word snapshot. If you only snapshot disk, rolling back can still leave you needing to reboot, restart services, or handle application consistency concerns. If you snapshot memory as well, you might preserve a more complete moment, but you also capture transient state that may not be stable across changes in host conditions or configuration. Linux Plus questions typically want you to recognize that snapshots are a convenience mechanism in the VM lifecycle, not a guarantee of recoverability in every disaster scenario. Snapshot management becomes even more meaningful when you consider how snapshots affect storage growth and risk over time. The copy-on-write model means that as the VM continues to run, new writes accumulate in the newer layers, and the base snapshot remains intact. This can create a situation where deleting a snapshot is not simply removing a file, because the system may need to merge changes or reorganize data to keep the VM consistent. Beginners often assume snapshots are free because they are quick to create, but the longer you keep them and the more changes you make, the more storage and complexity they can introduce. It also means that the VM's ability to access its data might depend on several linked pieces, so losing one layer can be catastrophic even if the base image still exists. From a lifecycle perspective, snapshots are best treated as temporary safety rails while you test changes or prepare for updates, rather than as a permanent time machine. The exam often encodes this lesson as questions about why snapshot sprawl is dangerous, or why a VM slowed down due to storage layering, and a student with the layering model can answer confidently. Migrations connect naturally to this storage story because moving a VM is really about moving its state, and the hardest part of state is usually storage. A migration might mean moving a powered-off VM by copying its disk image and configuration to another host, which is conceptually straightforward even if it can take time. A migration might also mean moving a running VM with minimal downtime, which is more complex because you have to deal with memory state, active connections, and continuous disk writes. Beginners sometimes imagine migration as dragging a VM icon to another server, but the deeper idea is that migration is a coordinated handoff where the destination must have compatible virtual hardware settings and access to the same storage state at the right moment. If storage is local to the host, migration requires copying large amounts of data or using a shared backend to avoid copying. If storage is shared, migration can focus more on transferring memory state and execution context. Linux Plus questions often probe this by describing a scenario where migration is easier when storage is centralized, because centralized storage reduces the amount of state that must physically move. To reason clearly about migration, it helps to separate two kinds of movement that are often mixed together in casual conversation: moving compute and moving storage. Moving compute is about transferring the running workload, including memory state and processor execution, from one host to another. Moving storage is about transferring the disk image contents or ensuring both hosts can access the same image. When storage is already accessible to both hosts through a shared backend, compute movement becomes the main problem, and downtime can be reduced because you are not copying the entire disk. When storage is not shared, you may have to move storage first, which can require a long copy, or you may have to move storage during the migration, which increases complexity and risk. A beginner-friendly way to think about this is that a VM is a combination of a brain and a body, where the brain is the running memory and execution state, and the body is the disk image and configuration. Migration is easy when the body is already present at the destination, and it becomes harder when the body must travel at the same time as the brain. This idea shows up on the exam as reasoning about prerequisites for smooth migrations and the consequences of storage design choices. The lifecycle perspective also includes what happens before and after migration, because a VM's identity and connectivity must remain meaningful during movement. A migrated VM that comes up with a different network identity can break applications even if the operating system boots perfectly. Similarly, a migrated VM that loses access to expected storage paths or has a changed virtual disk layout can boot into recovery mode or fail to mount important data. This is why migrations often require planning around consistent configuration and compatible device models, including the virtual network interface and virtual storage interface. In high-level terms, you want the destination host to present the same virtual hardware to the guest so that the guest does not interpret the move as a drastic hardware change. That stability reduces driver issues and reduces the chance of performance differences after the move. On Linux Plus, the important point is not the brand names of migration tools, but the concept that migration is an orchestration of state and compatibility. If a question hints that a VM moved but then networking failed, your brain should immediately connect migration to network mode and interface identity choices. Now we can turn to network modes, because network mode is how the host chooses to present networking to the VM, and this decision shapes what the VM can reach and what can reach it. Beginners often treat network connectivity inside a VM as identical to a physical machine, but the VM is behind a virtualization layer that can provide different styles of connectivity. One common mode is bridged networking, where the VM appears like a peer on the same network as the host, often with its own address on that network and the ability to be reached directly by other machines. Another common mode involves network address translation, NAT, where the VM can typically reach outward to the network, but inbound connections from the outside are not automatically direct because the host is translating and mediating traffic. There is also the idea of host-only style networking, where the VM can talk to the host and possibly other VM instances on a private network, but it is isolated from the broader network unless additional routing is configured. The exam often describes these patterns in terms of reachability, and the key is to map the symptom to the mode. Bridged networking matters because it most closely resembles plugging a physical machine into the same network as the host. In this mode, the VM behaves like a full network participant, which can make it ideal for servers that need to accept inbound connections from other devices. The trade-off is that it also exposes the VM more directly to the network environment, which increases the importance of host security, guest security, and correct addressing. Bridged mode can also involve network policies such as address assignment rules or security controls that are enforced on the physical network, so a VM may need to comply with the same expectations as any other machine. Beginners sometimes choose bridged mode to solve a connectivity issue without realizing they are also choosing a broader exposure model. From a performance and troubleshooting perspective, bridged mode can simplify path reasoning because traffic flows more directly, but it can introduce network dependency that can break a VM if the external network has restrictions. When a Linux Plus scenario suggests the VM must be reachable by peers on the local subnet, bridge thinking is usually the direction the question wants you to go. NAT mode matters because it reflects a different goal, allowing the VM to initiate outbound connections while keeping inbound access controlled and mediated by the host. In many learning environments and desktop virtualization setups, NAT is the default because it works in many network contexts without requiring the VM to be treated as a first-class device on the external network. The host acts like a gateway for the VM, translating addresses and managing the connection state, so the VM can reach the internet or other networks through the host connectivity. The beginner misconception is assuming that because outbound works, inbound should work the same way, and that is not how NAT behaves by default. If a VM running in NAT mode is hosting a service, external machines may not be able to reach it unless the host is configured to forward traffic appropriately. For Linux Plus reasoning, this often shows up as a scenario where the VM can download updates but cannot be reached from another machine, and the correct answer is not that the service is broken, but that the network mode changes inbound reachability. Host-only networking is often the easiest to understand if you treat it as a private hallway between the host and one or more guests. In this mode, the VM can communicate with the host on a network that is not directly exposed to the outside world, which can be useful for isolated testing, safe labs, and controlled management channels. The trade-off is that access to external networks is not automatic, so the VM may not be able to reach the internet or be reached by external machines unless additional routing or proxy behavior exists. Beginners can misinterpret this as a general network failure, when it is actually an intentional isolation design. From a lifecycle perspective, host-only mode can be stable across different physical networks because it does not depend on the external network's policies, but it also requires you to be deliberate about how the VM gets updates or communicates with outside services. Linux Plus questions that describe a VM that can talk to its host, but not beyond, are often hinting at a private network mode rather than a broken route. The skill is to recognize the reachability pattern and map it to the network presentation choice. Network modes also connect back to migration, because the more you depend on a specific external network behavior, the more careful you must be when moving a VM between hosts. If a VM depends on bridged mode to be reachable, the destination host must be able to bridge to the correct network in a compatible way, or the VM's identity may change and break clients. If a VM uses NAT mode, it may behave consistently for outbound traffic after migration, but inbound access may still depend on the destination host's forwarding behavior, which can differ. If a VM uses host-only mode, it may remain isolated in a predictable way, but any management tools that expect a stable connection path must be aware of the private network context. This is one reason lifecycle thinking is so valuable. Storage, snapshots, migration, and networking are not isolated topics, because changing one can indirectly change the meaning of the others. A snapshot of a VM taken before a network change might roll back configuration that affects reachability after migration. A migration might move a VM into a host environment where the network mode behaves differently due to policy. Linux Plus questions often test whether you can connect these dots rather than treating each term as standalone vocabulary. Storage choices also influence lifecycle operations like snapshotting and migration in a way beginners should understand at a high level. If your VM storage is local and large, copying it for migration can take time and can require careful planning to avoid inconsistency. If your storage uses a layered snapshot model, migration must account for the snapshot chain and ensure all layers are moved or accessible, or the VM will not have a complete view of its disk. If your storage backend supports shared access between hosts, migration can become smoother because the disk image does not need to be copied, but you must then consider the reliability and performance of that shared storage. You do not need to memorize specific storage technologies to understand this, because the underlying principle is consistent. The more the VM's disk state can be treated as a stable, accessible object independent of the host, the easier it is to move the VM's compute state. When a Linux Plus question hints that migrations are failing or slow, the storage architecture and snapshot complexity are often the hidden causes. A student who can say, the disk state is the heavy part, and it must be consistent, is already thinking in the right direction. As you bring these ideas together, it helps to keep a calm checklist in your head that is concept-based rather than command-based. If a VM storage problem occurs, you think about the disk image as the durable anchor and ask whether it is complete, accessible, and consistent across layers. If a snapshot problem occurs, you think about copy-on-write layering, chain dependency, and the difference between disk-only and disk plus memory captures. If a migration problem occurs, you separate moving compute from moving storage and consider whether compatibility and shared access are satisfied. If a network reachability problem occurs, you map the symptom pattern to the network mode and remember that outbound success does not guarantee inbound reachability. Most importantly, you remember that these are lifecycle operations, not isolated buttons, so a choice made early, such as storage backend or network mode, affects what is easy or hard later. This connected reasoning is exactly what Linux Plus is aiming to build, because it trains you to troubleshoot systems by understanding relationships rather than memorizing steps. By the end of this lesson, you should be able to tell a coherent story about a VM's lifecycle that starts with storage images and naturally includes snapshots, migrations, and network presentation choices. Images are the persistent disk bodies that carry operating systems and data, and they must be treated like valuable assets because the VM depends on them for continuity. Snapshots are branching points that can support quick rollback and experimentation, but they also introduce layered dependencies and are not the same as long-term backups. Migrations are coordinated moves of state, and they become much easier when storage is accessible at the destination and when the virtual hardware and network identity remain compatible. Network modes shape reachability patterns, so you learn to interpret symptoms like outbound works, but inbound fails as a mode implication rather than an application mystery. When you can connect these ideas cleanly, You will handle virtualization questions with confidence because you are reasoning from first principles about state, dependency, and presentation.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.